Welcome to today's webinar, Managed Database Options on AWS. Our presenter today is Scott Ward. Scott Ward is a Solutions Architect with Amazon Web Services. Based out of Seattle, Washington, Scott is part of a team that supports AWS's global network of technology and consulting partners. For AWS partners, Scott's focus is on existing AWS architecture validation and improvements, planning new architectures for workloads on AWS, providing guidance on how to use new AWS services, and providing general technical enablement. Today with us, we also have Lynn Ferrante, Business Development Manager, Databases, Radhika Ravirala, Solutions Architect, Abdul Sait, Principal Product Manager, and Clinton Ford, Senior Product Marketing Manager. They will engage with you and answer your questions throughout the presentation while our presenter presents. Scott, welcome. I now pass the floor to you.
Hello, everybody, and thank you for taking the time out of your day, whether it be morning, afternoon, or evening. Appreciate you listening in as we go ahead and talk about the managed database services that are available on Amazon Web Services. Quick overview of today's agenda. We're going to talk about quickly why would you want to use a managed database service, and then dive right into the relational, non-relational database options, the managed in-memory cache options, the data warehouse options, and then touch base on what some next steps might be for you to do if you want to look deeper into these managed services. So let's get started on why managed database services. Why are they important? Why could they be possible benefit to you? Well, there's a couple different options when it comes to running your database. It starts with self-managed. So with self-managed, you get full control of your infrastructure and the database engine that you're choosing, but you get to configure and you get to scale it as you want, as it needs to meet your application. But it also means that you bear 100% of the responsibility for making sure that the hardware is healthy, that the operating system and the database engine are patched appropriately, that backups are happening, and that replication is happening, and all the other pieces that go along with having a fully contained self-managed database. You can then look at maybe running your database on EC2 instances, and in this case, you really only, you don't have control over the infrastructure, as much control, but you still get to control the database engine, the operating system. You don't have to worry about that physical infrastructure anymore. You also get to take advantage potentially of some vertical scaling of your database, either up or down, at the push of a button that you might normally not get when you're running your database on premise. But you still have to focus on that operating system and database engine and some replication and backups and things like that. And then when you move to really more of a fully managed solution, you don't have to worry about any of the physical infrastructure anymore, the operating system patching, any database engine patching. You get to fully focus on actually using that database and integrating with your applications and your workloads. So let's quickly review what are some of the managed database options that exist here on AWS. You've got Amazon RDS, which is provide you SQL database engines, relational databases, Amazon DynamoDB, which is our document key value store, Amazon Redshift, which is our data warehouse solution, and then Amazon ElastiCache, which is our in-memory key value store. We will talk more about each one of these throughout the presentation that we're about to give. So none of these managed database services that I just mentioned are really going to be your do-all solution for all of your database needs. Instead, you really need to look at each of the services for what it does and leverage it for the right situation. Think of these services as a tool in your overall toolbox, and you're going to grab the right service to meet your current needs. So let's go ahead and get started with our first service deep dive and talk further about Amazon RDS, or Relational Database Service. So as the name says, it's focused on offering you a variety of relational database engines to use to support your applications. You get the option of 6 different engines to choose from. And for each of these engines, we support multiple versions of the engine. Today, you can choose from MySQL, Postgres, Oracle, SQL Server, MariaDB, and Amazon Aurora. With each of these options, AWS is taking care of the management of the infrastructure and the operating system and the database engine. And that includes minor and major patching that might be related to each of those engines. It's simple to use because in just a few clicks through the management console, you have a database up and running and ready to use with your application in just a few minutes. It's fast to scale because, once again, with just a few clicks of a button or some API or command line calls, you can choose to resize your database up or down to meet the current demands being placed on your database. And finally, it allows you to have a low cost through a pay-as-you-go model. So you only pay for the storage that you're provisioning for your database and the amount of time that your database was actually up and running. Some common use cases when it comes to relational databases. Relational databases have been around for over 20 years, so it makes sense that they crop up in a lot of different use cases. They have good use cases for supporting a lot of different industries as well as a lot of different types of business functions. When you think about industries like e-commerce and gaming, they take advantage of relational databases. And there's lots of applications that are built to use a relational database as kind of the back-end store for the application. And there's lots of homegrown IT solutions that have evolved over the year that at some point needed a data store, and they're leveraging that relational database as well to support that. And then reporting, it can be really a key function of a relational database. It allows you to kind of report on data that maybe you're using the relational database to back an application, or it could even be a data store for multiple applications or workloads where you're using that as a common spot to be able to query the data out of the database. Here's a feature matrix for RDS right now and the 6 different engines that are supported. And so you can see that among those 6 engines, there's a lot of features that are very common among all those engines, but there's also some differences around what you can do. The big thing here is that from a managed service perspective, you can do a lot with each of the engines, and your decision often comes down to really the specific functionality that you want to get out of that engine, or if there's a particular competency that you have around a particular database engine that you want to continue to use as you're using it on AWS. One specific engine that I want to speak to a little bit more is Amazon Aurora, because it does have some pretty big differences when you compare it with the other engines. This is a relational database that was built by AWS with a focus on optimizing for cloud-like resources and really designing that database to work in the cloud. When it comes to performance, Aurora benchmark testing shows that it's 5 times faster than MySQL running on the same hardware. Additionally, we did some testing using the industry standard Sysbench product for MySQL testing and found that it could actually achieve over 100,000 writes per second and over 500,000 reads per second. When it comes to storage, every piece of data that Aurora writes, it writes 6 copies of it across 6 different storage nodes across 3 different availability zones within an AWS region. So in the end, every availability zone has 2 copies of every piece of data, so you are protected from the failure of any one particular availability zone. Anytime that there is a read and write that happens against the data, Aurora does a quorum. For writes, it needs a response from at least 4 of the storage nodes, and for reads, it needs a response from at least 3 of the storage nodes before it can consider that operation to be successful. When it comes to actually being able to store your data, you can store up to 64 terabytes of data, and that storage will naturally grow with you as you use Aurora. You don't have to provision an initial amount of storage. You just start using it, and the storage will grow as you start to use it. And then to help you with read performance, you can actually have up to 15 read replicas that are also tied to that overall storage for your production cluster and helps kind of relieve any pressure that you might have on your master. So it's simple and it's fast to scale. As you can see, with a few changes in the management console, you can change the size of your instance up or down as it relates to CPU and memory by just choosing a different instance class. There's lots of different reasons why you might scale your instance type. You might scale up to handle some increased demand that's happening on your database, or you might scale down back to a normal size after a large event's over. Or you might even scale down over the weekend when your database is really heavily underutilized and you don't want to actually pay for the database that you would run during the week. You can also add storage to your database instance, and keep in mind that you can only add storage, you can't take it away, but if you start out small and you're continuing to grow, you can continue to add storage to your database over time. What you see here is actually a screenshot of the management console, but it's also just as possible to use the command line interface or the software development kit to actually be able to modify your database instance with just a few parameters in the overall call. It also offers fast and predictable storage. So there's 3 different storage types to actually choose from when you're launching an RDS instance, and this is the 5 engines that are not Aurora. So you have the general purpose SSD storage, which is very suitable for a large different array of workloads. You get a baseline of 3 read-write operations per second for every gigabyte of storage that you provision, with the ability to burst up to 3,000. And this storage really gives you the option to have a good ability to handle some spiky workloads or spiky events that may happen. We also have the provisioned IOPS storage, which allows you to actually provision a set amount of read-write operations that you want to have happen every second throughout your the life of your database, and it gives you some very consistent and predictable performance for the workloads that you're using that database engine. And then you have the standard storage or the magnetic storage, as we refer to it, and it's really useful for some small database workloads where you need the data there, but it's really accessed pretty infrequently, and you don't need the high performance that you might get out of the solid state drives. So when you're launching your database instance, you can choose which storage type is right for you upon really the initial creation of that instance. And if you determine that a different storage option is better for you as you start using the database, you can actually change the storage type that you want while your instance is running, and kind of, as you saw on the previous slide, through the same process, really modify that database engine to switch to a different storage type after you've observed how things are performing on the current storage type to better optimize the performance of your overall database. So another key piece that you want in place for a production database is to make sure that it's highly available and that it can really withstand failures that might be happening throughout the infrastructure and the facilities that are potentially even supporting your infrastructure. So RDS offers you the ability to configure your database instance in what we call a multi-AZ or a multi-availability zone configuration. So with this configuration, you'll have a master RDS instance that is responsible for handling all the reads and writes against your database. At the same time, the RDS service will provision or have another EC2 instance as the standby in another availability zone of the overall AWS region that you're running in, and it will also provision the same type and amount of storage as you have provisioned for your master database instance. So then at this point, RDS works to keep your data in sync between the master and the standby instance, and then anytime that there is a problem with communication to the availability zone that the master's in, or there's a problem with the health of the master instance itself, the RDS service is actually going to switch the DNS endpoints that point from your primary to make them point to the standby instance so that you can continue to be up and running and have little to minimal downtime as a result of a failure related to your master database. So, and all of this happens without any action from you, resulting in you being able to kind of focus on your application once again and reduce the operational overhead that you might have when you're managing more of an on-premise or unfully managed database solution. So, read replicas. One of the pressures that can be placed on a relational database is supporting a large number of reads against the database. And this becomes challenging for a database when it also needs to support handling write operations and all the integrity checks that the database has to enforce along the way as it is reading and supporting reads and writes of data. So one way to ensure that your master database isn't overloaded is by doing all this work is to actually offload those read tasks to another database. So RDS actually offers you the ability to create read replicas for MySQL, Aurora, MariaDB, and Postgres databases. You can determine the availability zone that these read replicas are in so that you're actually maintaining a high availability strategy for read operations on top of that. So when you take this approach, you have another RDS instance that's dedicated to supporting all the read operations that your applications or maybe your organization may have against a particular data store. And on top of this, you can also create multiple read replicas to support many read operations if needed. So if there's different applications or different groups that all need access to the same data and their needs are large enough to justify multiple databases, you may actually have multiple read replicas to support each of those requirements. Another interesting thing about read replicas is these actually can be promoted to be a master database. So if there's some problems with your master database, you can actually promote a read replica to be the master, which will actually help in reducing downtime when you have issues with your master database. And you can also choose cross-region replication for these read replicas. So if you're using a MySQL or MariaDB, you can actually have your read replicas in a different AWS region than where your master database is right now. So this allows you to get your data even closer to your end users or your customers if they're geographically in different locations from maybe where your primary data store is. And it also gives you the ability to have your read replica promoted to a master in a different AWS region. It's part of a migration or potentially a failover effort. So staying on the cross-region subject, you can also take snapshots of your database and copy them to different AWS regions. So with this approach, you can actually have a copy of your data stored in another AWS region to support maybe a disaster recovery effort that you have, You could even go a step further and actually have a warm standby where you're not only taking a snapshot or a point-in-time copy of your database and copying it to another region, but you're also actually in that new region launching a new RDS instance based on that snapshot, so you have that database actually up and running to handle potentially even a faster failover time to a new database in a new region. So let's talk about, I've mentioned backups and snapshots. Let's talk about those for a minute. So backups are enabled by default when you create an RDS instance. You can choose the time that you want the backups to happen, and they're actually retained for up to 35 days. And they allow you to restore to a point in time. So when you initiate a point in time recovery, you actually will create a new RDS instance that will be based on that newest backup that's closest to your point in time, and then the additional transaction logs that have happened since that last backup will also be applied to allow you to restore to that point in time. These backups are free as part of the overall RDS service. And then you can also take manual snapshots, which are initiated by you as a user, and they enable to take a copy of your database from a known state really as frequently as you want to. If you want to do it once a day or once a quarter, you can then take these snapshots, and they stay around as long as you want, and they're backed by S3, and you can take these, you copy them to another region, as we already talked about for disaster recovery, but you can also use these snapshots to support creation of another database, maybe for non-production efforts. Say you're taking a copy of your production database and you want to enable your test or your QA or your dev team to be able to do work against something that's more production-like to help give them a better chance of success, that what they're building and testing is actually going to be more successful in production because it's working more closely aligned with production-like data. So it allows you to have that good data set to work against for non-production uses as well. So when it comes to pricing on RDS, as kind of the well-known AWS model, you only pay for the resources that you're using. So your monthly bill for an RDS instance is really going to be made up of the time that that database instance was actually running, plus the amount of storage that you actually provisioned for that RDS instance, all of that multiplied by the number of RDS nodes that you're running. If you're just getting started with RDS, take a look at the free tier. There's called out in the bottom left corner. You have many number of hours as well as backups and I/O operations, and that you can use to actually test out and see how RDS works and see if it's a good fit, or try different configurations to see what works best for your applications and your workloads. Here's a select small representation of some AWS customers who are actually using RDS to support their applications and workloads running on AWS. Flipboard, they're an online magazine with lots of millions of users and then really billions of what they call flips per month, and they use RDS and its multi-AZ capabilities to store their mission-critical user data. And they went really from a concept of delivered product in 6 months with just a handful of engineers. So with minimal resources, they were able to get a very large scale website and company operating on RDS. Another one is Samsung, where they actually deliver application and content from RDS. And they were actually able to, by using RDS, save 85% of costs over the on-prem solution that they were using to support this prior. All right, so let's move on to Amazon DynamoDB. So Amazon DynamoDB is our NoSQL database. When we talk NoSQL, it's a pretty common use case that you hear these days, and it really refers to what you would consider unstructured data, which is data that may change in format and content from record to record that you have stored in a table. You don't have to worry about getting all of your data to fit in a defined schema as you might have to do with a relational database. It offers low latency for reads and writes, allows you to scale up or down immediately, and it delivers this at a really low cost when you compare with what it would take to implement and support a comparable solution on your own, or even using cloud infrastructure. We'll actually dive into some of these a little bit deeper. So it's simple and fast to deploy. So via the management console, the command line interface, the SDKs, you can actually define a new Amazon DynamoDB table and all the proper configuration you need with just a few clicks of your mouse or a few lines of code. And then once you have your table created, you can make changes to allow your table to scale for read and write operations that you're running against the table. So if your table is becoming more write heavy or read heavy, you can actually adjust the amount of throughput you want to allow for your table real time to allow you to be able to scale up and down to the needs of your application and your users. Once again, that can be done through a quick couple of clicks in the management console or via the command line interface or the SDKs. The data that you store in DynamoDB is automatically replicated to help with availability and durability. And your performance is very predictable and consistent through the use of solid-state drives that actually store your data to provide you a lot of low latency performance and really help ensure that you are getting predictable throughput both on your read and write operations. To allow for fast lookups of your data, there's also things that we call secondary indexes that you can implement, and we'll actually talk about those in a few more slides. And when you create a DynamoDB table, there's no actual cost for creating a table. You actually only incur charges when you actually start reading or writing and storing data into DynamoDB. So there's some popular use cases for DynamoDB, and there's lots of ways to use it. So this list is certainly not an exhaustive list, but it's a good way to show that there's lots of different ways and industries and companies that are actually using DynamoDB today to support some very large-scale operations. So you start with like ad technology. They might be using that for delivering targeted ads, keeping track of user profiles, or even maintaining some session state. When you look at Internet of Things, that's a very hot term these days. They might use that for tracking the metadata about a particular device. Think about millions of devices that are constantly trying to communicate and say, here I am, or here's my current state. Potentially also being able to support the ability for a lot of devices sending that data in at the same time. When you look at the gaming industry, you look at recording the details about a game or keeping a real-time leaderboard, maybe even maintaining state on each of the game sessions that are happening for a very large online player game. And then the mobile and the web space, once again, looking at things like storing like user profiles, session state once again, and even metadata about specific devices that are being used to interact with your application. So a few slides ago, I talked about that automatic replication of your data. So when DynamoDB receives your data via a write operation, that data is actually replicated synchronously across 3 different availability zones within that region that your DynamoDB table is located in. Then when it comes to reads, you can choose to have eventually consistent reads or strongly consistent reads. So when you read your data, if you're looking for eventually consistent, it means that if you write a piece of data and then you read it right away, you may not get back the data that you just wrote or the data that you updated until it's fully replicated across all the availability zones. You may have to wait to reread the data to ensure that you have the most up-to-date data, or you may have to wait a few seconds before you actually do the read to ensure that you've got the most up-to-date data. If you ask for a strongly consistent read, the read operation will actually make sure that you are getting the most current copy of the data when you actually run that get item API command. So we talked about DynamoDB being a schemaless database. So what that means is that there are multiple items that are stored within one table, and they may have a different number of attributes that actually make up the record that's stored within that table. So each attribute for an item that is stored in a Dynamo table is represented by a name value pair. So if you're storing a city, you would store a key of city and a value of city name. When you're creating and defining your table, you actually have to define a hash key or what we call a primary key. It's a unique identifier for each item that you're storing in the table and ensures that no 2 items can have the same key. This allows you to be able to retrieve information about each item quickly, and DynamoDB is actually able to maintain an index that allows it to find and retrieve that data very quickly for you. With your primary key, DynamoDB actually makes a hash and determines which partition in its data store to store the particular item, and it allows it to evenly distribute that data across multiple data stores and ensure that data can be accessed quickly and that no one particular area of the data store gets overloaded. Think about this table maybe as containing a list of orders that are made on a website. For this table, we might use the order ID as our hash key or our primary key to be able to actually pull each order up individually quickly or make changes to it. Optionally, after you've defined your hash key, you can also define a range key that's an additional index that you can query against. When you define and populate this key, Dynamo uses it as another input in determining where to store that data physically so that related items are all kept close together and can be accessed quickly. Let's say that in this table you have your orders once again, and for that retail website, and your hash key is once again that order ID. Your range key might be the date that the order actually happened on. So when you write the data to the table, each item would have a unique hash key of the order ID, but they might have overlapping range keys of the date. But it would allow you to actually not only be able to quickly query for an individual order, but maybe for all orders that occurred on a particular day. Another thing that you can do is actually create local secondary indexes. So, you're planning out your table, you have a rough idea what your hash and your range key might be, but over time, as you're using your table, there might be other attributes that actually become very important for you to be able to query on that haven't been defined as a hash or a range key. So what you can do is look at actually creating local secondary indexes to allow you the ability to actually focus and search on these other attributes through an indexed way so they can be retrieved quickly. So they give you the ability to define alternate keys that you can query your scan against, and it gives you that more flexibility for querying that data. With a local secondary index, you would actually define a new partition index and range key based on the attributes that exist in that table. And it allows you to be efficient at multiple queries that are going to be happening against your table so that your workload doesn't slow down or your application can keep up with the pace of the requests that are coming through from your end users. So when you specify that local secondary index, you specify which attributes actually you want copied over to be represented or projected from that base table into the new index. And at a minimum, the key attributes from the original table, as well as the new index attributes are projected, and then you can choose additional attributes that are not part of the index that you still want to be made available to be displayed when you're querying against that local secondary index. So in order to really be able to get you that desired throughput for DynamoDB, you're going to need to be able to configure the throughput for both the reads and the writes that you want happening against your table. So for each DynamoDB table, the throughput for reads and writes is configured independently. So you have the flexibility to really be able to scale on what is the most important and necessary for that particular table. So what are these read and write capacity units? Well, for writes, you're defining how many writes you expect to happen against your DynamoDB table in any second for item sizes up to a kilobyte in size. And then for reads, you're defining how many reads per second you're going to have up to a size of about 4 kilobytes. And when you're defining that read capacity, there's actually two possible ways you should keep in mind. One, with your per second configuration, you can get one strongly consistent read per second, or two eventually consistent reads per second. So if you remember back to a few slides ago, we talked about the eventually consistent or the strongly consistent reads. Those factor into how you configure your read capacity throughput based on the types of reads that you're going to actually be executing on. So keeping in mind, provisioning and creating these, if you start to have more transactions, whether it be from a write or a read perspective, then you have defined throughput, you'll start to see backlogs or delays in being able to get all the data through at the point in time that you want it to, which will potentially lead in unhappy service or customers or delays in getting things processed. So you'll need to keep an eye on how these metrics are being used and potentially adjust up and down throughout the life of the table depending on how it's used. Here's a very, very simple architecture example using Amazon DynamoDB. So you've got various clients, whether they be somebody on a laptop or mobile devices, connected to an endpoint going through an Elastic Load Balancer, which is then connecting with a cluster of Amazon EC2 instances that represent your application. And then those instances are actually communicating with a DynamoDB table from both reads and writes, and then returning the appropriate information back to the original clients who sent the information. So billing in Amazon DynamoDB is a little bit different than the other services that we've talked about or are going to be talking about. So we're going to take a couple slides to talk about this. With Dynamo, you're charged for the amount of storage that you consume, and then you're also charged for the amount of write and read capacity that you've provisioned for that particular table. So in this example here, we've got 5 gigs of storage that we've consumed. We've got a write capacity of 21. We've got a read capacity of 35. Assuming usage throughout the entire month, each of those at 720 hours, So to be able to support that DynamoDB table, we have a total bill of about $14.36. If we then move on, we start to look at the free tier. You'll see the free tier is a common theme throughout this presentation. So with the free tier, you get 25 gigs for up to 12 months. You get 25 gigs of storage, 25 write units, and 25 read units. So you can start to see that the free storage will cut into the overall cost and reduce the amount that you're actually charged for the storage, the reads, and the writes, which actually results in this slide where you have an end result of a total charge of 94 cents to support how you're using that table for any one month, any particular month. So as you're getting started or curious about DynamoDB, I encourage you to kind of pay attention to what the free tier constraints are and try and work with those in to kind of really minimize the costs that you have, but kind of maximize the ability for you to be able to understand and play with DynamoDB. And here's a sample of customers that are using DynamoDB today. We'll talk about a few. Redfin, they have over 5 billion items that are actually stored and processed daily in DynamoDB. SmugMug, they're the photo hosting and sharing platform, and they've got millions of users and billions of photos and petabytes of storage, some of that using DynamoDB. Dropcam, they have a video streaming solution, and they actually are able to reduce the delivery time of video events from 5 to 10 seconds to a few milliseconds through incorporating DynamoDB into their overall application architecture, and has offers. They're a near real-time mobile and web marketing platform, and they've got lots of data providing ad hoc analysis, and they have over 2 billion items covering about 87 terabytes of data within their DynamoDB data store. So we've talked about relational databases and NoSQL databases, and so there's a common question that comes up of really, how do I choose? Which one is right for me? What should I be using? Should I be going with the new hotness of the NoSQL, or should I be sticking with the relational database? Well, it really kind of comes down to what you want to use, but there's a few things we can talk about that are pros and cons of each one. So when you talk about NoSQL, it's schemaless, as we talked about. So it's pretty easy if you'd be able to do reads and writes and create a very simple data model, because you're not constrained by maybe a more rigid schema that might exist in a relational database. Scaling is easy because you can dial up and down your read and write operations. And DynamoDB is really focused on performance and availability at any scale. When you look at RDS, it's got a very strong schema. It can support very complex relationships and transactions and joins, which might be necessary, especially for some online transaction processing applications. Scaling is a little bit difficult. You can do some vertical scaling, but you can't really scale out horizontally to add more and more resources to support a larger load. And the SQL and relational databases really focus on that consistency of making sure that the data integrity over scaling and availability. So let's go on to the third member of our managed services today, which is Amazon Redshift. So Redshift is AWS's relational data warehouse service. And with all the other services we've talked about, Redshift is also fully managed, allowing you to really focus on what you would be doing from a data warehouse, really modeling, loading, and querying that data. Redshift, it works in a cluster configuration, allowing the allocation of work to support data loads and queries in parallel among many compute instances, as well as taking advantage of not only the instance, but all the CPUs that actually exist within each of those instances to get all of this working together to do as much work as possible in parallel as quickly as possible. Allows you to grow and store a large amount of information, allowing you to get all the way up to a petabyte of scale of data. And there's two different platforms. They're focused on either being able to store a large amount of data or be able to focus on getting you faster access to that data. You can use, if you've got some favorite BI tools or an on-premise data warehouse today, and you've got certain BI tools that use ODBC or JDBC connectors, you're probably going to be able to use those with Redshift. So if you've got a really, really favorite tool you're married to, you're more than likely going to be able to use it still. And at the end of the day, this service really gives you a very economical solution for a data warehouse with costs as low as $1,000 for every terabyte a year. And think about the costs and the operational challenges that go with running some very large-scale data warehouses on-premise versus some of the things that you're going to see here from the Amazon Redshift service. So who uses Redshift? at a very high level, there's lots of different use cases as far as who might be using it. You've got your traditional enterprise companies who want a data warehouse, and they might use Redshift rather than like building or extending their existing data warehouse. They might actually just burst into AWS and create a new data warehouse to support new needs and situations that they have while maintaining their on-premise one. They might migrate completely away from their existing data warehouse systems and start using Redshift. And it allows them to really respond faster to their business because they're not having to worry about ordering and provisioning and waiting for that infrastructure to show up. They can provision a new cluster and start putting data into it and start using it right away. Companies in general that have big data, it doesn't have to be an enterprise, it really gives them the ability to improve performance by an order of magnitude because they can create a very large cluster or make a cluster even larger to be able to support the needs and the performance requirements that they have. Make more data available for analysis. They're not having to worry about juggling how much data they can put into a on-premise storage solution because you can create larger clusters with Redshift or create multiple clusters to be able to make all your data available and really access that business data via standard reporting tools as we talked about earlier. You can use your favorite BI tools. And then software as a service companies, they actually are using Redshift to add more functionality into their applications because they can provide more rich, broad data about the data that their end users have given them and are asking them to store. And then as their user base grows or the demands or they release some new functionality, they can actually scale that data warehouse to continue to grow with the demands that are there with just a few clicks of a button. And it really allows them to kind of keep that software and hardware costs low and provide a service for a lot of people all at the same time. So here's a quick overview of the like a generic Redshift architecture. As I talked about before, it starts at the top with the BI tools. So your favorite tools using a JDBC or ODBC connection. Those are then going to connect into the leader node. The leader node, you're always going to have a leader node with a Redshift cluster. It's a very simple endpoint for your BI tools to connect to. It stores all the metadata about what's going on in the Redshift data warehouse and where data is stored. It's working on optimizing the query plans that you pass into it, and it coordinates that query execution across all the compute nodes that you see further down. So then those compute nodes, those are the ones that are actually storing the data that's queried. They use a local columnar storage, which we'll talk about in just a minute. And these are the things that can actually do the parallel execution of your queries and your loads and your backups to allocate work across all of the compute nodes as well as all of the CPUs that exist in the compute nodes to get things done as quickly as possible and reported back to that leader node so that you can then go and return that information back to the SQL and BI clients. And then we have, at the very bottom, we have Amazon S3, DynamoDB, and Amazon Elastic MapReduce, which can all work as data sources for ingestion of data, as well as S3 will also be your source for backup and restore, and we'll actually talk about that in just a minute. So there's a few different ways that Redshift actually is able to reduce the amount of I/O or read-write operations that have to happen to actually be able to return your data and, in a result, give you your data back faster. It starts with the use of column storage. So there's in a storage solution that's using maybe a traditional row storage, you have to read all the rows in a table in order to get at the data in the column that you're ultimately querying. So this results in you reading a lot of data that you don't even need, even if you're not going to use it. So with the column storage, you're only reading the data that you ultimately need to get to. So here's an example of column storage where the same table we had on the previous slide where I just want to query the amount column. Maybe I want to see all the amounts, maybe I want to see a sum. But with column storage, it's going to go directly to the amount column and just give me all the information about the amounts that are there. It's not going to worry about the ID, the age, and the state columns or give me all the rows of data that I don't need. I just need the amount information, so it's going to give that and return that back to me very quickly. Additionally, we talk about data compression as part of another way that Redshift reduces the I/O that's needed. What it does is that it scans the first maybe 100,000 loads and picks up the best compression algorithm encoded for each of the columns based on the data sets that have actually been loaded. And so what we've seen from customers when we talk about the data compression is that they've seen a 4 to 8 times space savings with their real world data sets. Depending on the data, some columns are going to compress more than others. But an example might be that if you have about 4 terabytes of data, that can become about a terabyte of data in a Redshift data warehouse. And so that means less storage, so there's less cost for the storage, but it also means that A read of data is able to get more data back because all that data is located closer together, which actually leads to better performance in returning the results of your queries. Zone maps is another way that I/O is reduced. So for columns which are sorted by maybe a sort key, Redshift keeps track of the minimum and maximum values of each of those keys for a block of data. And so when you execute a query against those keys, it knows within the range where that data is stored, and it allows it to get to that block of data faster to be able to once again get the data back more quickly for a query. And then direct attached storage. So when Redshift reads from disk, it makes them as high performance as possible by using that direct attached storage. The drive and the CPU and the memory are all local for those reads. So it's able to get that data. It's not worried about going across the network or anything. It's focusing on that high throughput that exists on that local compute node where all the data is. So when it comes to backing up your data, there's a multiple features that are actually in action when it comes to Redshift. So when your data is stored in a Redshift cluster, there's multiple copies of the data that are stored within the cluster, helping to protect against any data loss. Redshift also is continuously backing up to S3, so you get the benefit of the availability and durability that comes with S3. If your policy around data protection actually require that you actually back up to multiple regions, you can actually configure your Redshift cluster to not only back up to S3 in one region, but also back up to S3 in another region. So at any point in time, your data will be backed up and actually used and stored in multiple regions. It'll actually allow you to restore from another region if you have an issue with restoring from your primary region. It also offers a lot of fault tolerance when it comes to Redshift. So it can detect a drive failure. It can automatically begin using another in-cluster copy of that data, so the drive that serves queries that's unhealthy is not taken into account, and it also works on replacing that data. If it detects a failure that requires a node to be replaced, it automatically provisions and configures a new node and adds it to your cluster so you can resume operations. Snapshots are stored to different availability zones within a region to make sure that they're highly available. And the multi-region backup can actually be used once again to handle any global disaster recovery efforts that you might have. So with Redshift, it's very similar to the RDS model from a pricing perspective. You pay for the amount of time that each of your compute nodes were running. You don't pay for the leader node, times the number of nodes that were actually running. A quick thing to call out once again is there is a free tier for RDS. It's a 2-month free trial, 750 hours of the DC1 large. Now, if you create a multiple node cluster, that's always going to get cut in half. So your 750 hours would get cut to 375 hours if you were running a 2-node cluster. Here's a quick overview of the ecosystem of partners that Redshift works with right now. So if you're looking at data integration or BI tools or even consulting partners that might help you out from a Redshift perspective, there's a large amount of companies that we work with today that can help you provide those services. And then here's a quick review of the customers that exist on the Redshift side. It's a very small selection once again, but a quick overview. NASDAQ, they load billions of records per trading day to actually be able to track client activities, and then they use Redshift for that. Nokia was actually able to go to Redshift, and they found a 50% reduction in the overall costs that they were using to support their on-premise data center. And finally, but certainly not the least of all of them, is Amazon ElastiCache. So ElastiCache is our once again, managed solution for being able to cache key data to enable performance improvements within your applications. We offer 2 different engines to choose from, either Memcached or Redis. So if you're using either of these engines today in your own on-premise environment, you can actually continue to use them in AWS without the extra task of managing the infrastructure that's actually needed to support these solutions. As a managed service, you actually have the ability to configure the environment to meet your needs, and you can start small and then grow into a larger cluster of cache instances to support your data store and your query throughput requirements while only paying for what you're actually using. So some popular use cases that come along with this, certainly a caching layer for increasing performance of an underlying database, so it allows you to reduce or eliminate the amount of time that you have to go back to the database to query information. You might use it for storage of ephemeral key data. Maybe there's some key data that you want to keep around. You don't need to keep it around for long. You might use one of the ElastiCache options to actually store that data for a period of time and allow you to be able to get to it quickly for maybe the life of a session. And then there's some things like leaderboards or session management, some of the things we even talked about from a Dynamo perspective, where you might want to use a caching layer to be able to support the ability to access that data quickly and consistently. So a couple of key features for each of these engines that we support. As we mentioned before, it's fully managed, so you really just focus on management of the actual cluster software. With Memcache, you get the ability for some automatic discovery of new nodes that are launched into that cache cluster, which is done by your application connecting to one node to discover about all the other nodes that are available in the cluster. Then your application can actually maintain a list of all the nodes that it wants to communicate. With Memcache, you can also locate all the nodes within one availability zone or spread them out across multiple availability zones to give you more of a high availability configuration and protection against failures in any one availability zone. With Redis, you can group your clusters into a replication group where your data is actually replicated to read-only clusters, helping you to protect against data loss within that main cluster. These clusters, once again, can be spread across multiple availability zones to kind of give you that high availability configuration. And with Redis, you can also back up your data. So these backups can be used to restore a cluster or actually be a starting point for building out a new cluster. And these backups are all stored within S3, giving you the high availability and durability that comes with S3 to kind of give you the assurance that your backups are going to be safe. There's a lot more that the ElastiCache team is doing for these services on a regular basis, so I highly encourage you to check out the product pages for this to kind of see where they are now and where the features are based on the type of engine that you want to use. So here's a very simple application architecture that's using ElastiCache. Very similar to some of the other ones. You've got clients connecting in through an endpoint through Elastic Load Balancing, going to some Amazon EC2 instances. Those instances at that point might be reading from an RDS instance, but they're also relying on the caching layer now to support reoccurring or common data queries that they might normally getting from the database engine, allowing them to get responses much faster than they would get from the same query over and over again against a relational database. Here's that same architecture, but blown out to be much more resilient. So now we've got the load balancer balancing across EC2 instances in multiple availability zones. They're each going against caching clusters that are in multiple availability zones, and we've also got an RDS configuration that's actually using a multi-AZ configuration as well. So each of these layers is actually protected from a problem or a failure within any one particular availability zone. ElastiCache billing, very similar to some of our other services today. You charge for the duration that any one particular node was up and running, multiplied by the number of nodes gives you your overall monthly bill for any particular caching cluster. Once again, there's a free tier. So for the first 12 months, you can get 750 cache node hours for a micro node to allow you to, once again, test out and see how ElastiCache works and figure out what's the right configuration for you at a very low to minimal cost. Some selected customers that we have that are using ElastiCache today, we have Expedia. They have a 400 node cluster of ElastiCache right now. Riot Games, they use ElastiCache Redis for their League of Legends game, which is one of the most played PC games in the world. And Adobe, they're using Memcache for their shared cloud service. They're managing counters that are not really persistent, but that are needed for a particular amount of time to support the service that they're offering up. And finally, I want to take just a quick minute to kind of take all those different application architectures that I've shown and kind of combine them into one using all the different managed services I've had. So we have our clients coming into the Elastic Load Balancer, distributing traffic to EC2 instances. And in this example, I've actually got the EC2 instances using DynamoDB as their session state. So they're able to read and write very quickly from that table to kind of keep track of what's going on from a session perspective. And then these clusters are using ElastiCache to actually kind of figure out or get their query information very quickly instead of going back to the relational database every time. We've got both our relational database in a multi-AZ configuration so that we are writing to a master, but we have a standby in place and in sync with a master. And then finally, we have Redshift being fed from that master database so that our end users are able to perform the queries that they need to understand what's going on and help make some business decisions about the overall application in the company. So next steps for you. We've called it out before, but I want to call out once again the free tier. Each of these managed services has a free tier, allowing you to be able to go in, provision some resources and actually start playing with them and using them and understand how they work and see how it is a good fit for you and your application workloads. So I encourage you to take a look at that. Then the next step, I encourage you to take a look at the public documents for each of these services, especially the FAQ for each of these services. I find that as a great source of kind of quickly learning more about what that service can and can't do, and maybe even getting some of your initial questions answered. All right, so that kind of covers everything today from a very high level on these managed services. There's a lot more you can dive into with each of these, and those almost cover a whole webinar on their own, each one. I'd like to thank you for kind of listening in today. I hope I answered some questions for you and gave you a good idea of where these managed services sit and where you might be able to go. Well, I think that wraps up the time that we have today for the webinar, so we're going to close things out here today. I've really enjoyed doing this. I appreciate everybody listening in. And once again, I hope it was very beneficial to you, and thank you very much for your time.